Today we're going to continue our study of linear algebra by looking at eigenvectors and eigenvalues. So we're going to start doing that with this visualization tool hosted on GitHub. And we're asked to look at the matrix 4, 1, 1, 4. And the way we control the matrix entries here is by controlling these two red and green targets, which specify the images under the transformation of E1, which is the green vector pointing in the horizontal direction, and E2, which is the standard basis vector in the vertical direction. So if we want the first column to be 4, 1, then we need to move this point here, and it's a little hard to get it exactly right sometimes, so we'll snap to grid. And then the second column we want to be 1, 4, so we move this red point up here. And we can visualize the transformation by moving the slider. So the t equals 0 corresponds to the domain, so all the points you see other than these two targets correspond to where they start out before the transformation is applied, and then they just move in a linear way directly to their destination. So as we move the slider, the red and green vectors go where they go, and then everything else goes where it has to go to enforce linearity. So that creates a grid structure on the image side. So this is codomain and this is domain. So the question is, how do we visually identify the eigenvectors here? So maybe it's easier to start by saying what clearly isn't an eigenvector. E1 is not an eigenvector because it gets turned. So the image is not parallel to the starting vector. So that's definitely not an eigenvector. We can look at another vector like 1, 1 and see where it goes. And actually, we got lucky on our first guess. We found an eigenvector. That vector gets stretched under the application of the transformation, but it doesn't get turned at all. So that's one eigenvector. And we can look around for other ones, like maybe we try this point, and that one gets turned to the right a little bit, so that's no good. Let me try this one over here, and that one gets turned as well, but not very much, so maybe we're pretty close. So we try something like that, and that one gets stretched also. So we found two directions of eigenvectors, and we can actually just show this in the picture, take the yellow one out, and they show up in orange there. So it's the two diagonal directions in this case that get preserved. So another matrix we're asked to look at is -2, 1, -1, 2. So the first column is -2, -1. So the green should get dragged to -2, -1. And the red one goes to 1, 2. And in this case, we see some different behavior. The points get flipped around. So if you drew a picture somewhere here on the domain side and saw where it goes on the image side, it would get reflected. Oops. So if we're looking for eigendirections here, it gets much trickier to track with your eye. So we can try some examples. That one gets turned a lot. That's no good. Let's try the diagonal direction. That gets turned a lot. Looking in the picture, seems like maybe something over here might be closer. And yeah, that's looking better. It gets turned a little bit, but it's pretty close. Maybe try this one. Okay, that's looking really close. Let's just give up and show the eigenvector directions. So we're really close right there, and then there's another direction, sort of here somewhere. It gets preserved. And notice that in the previous case, the eigenvectors were orthogonal to each other, and in this case they aren't, and that's connected to the symmetry of the matrix. So this is not a symmetric matrix, so its eigenvectors are not orthogonal. And the other one was symmetric, so its eigenvectors are orthogonal. That's the spectral theorem. So finally, we're looking at the matrix with the first column of 2, -2. and a second column of 1, 2, which is already there. And we're looking for eigenvectors here, and it sort of looks like everything gets turned. In the picture, it's not a pure rotation because there's some scaling, and the scaling happens a bit differently in different directions, but still the net effect is a rotation. And if you look at any vector and see where it goes, it's going to rotate. So this one looks like it doesn't have any eigenvectors, and actually what you can see of this tick box is that I never stopped asking it to show us eigenvectors, and it's not showing us any, so that suggests that there are none. So this is a different situation still, and what we can do is come back to Julia and use the eigenfunction to take a look at some of these matrices and what happens from a spectral point of view. In other words, from an eigenvector eigenvalue point of view that corresponds to what we saw over there. So if we look at the eigendecomposition of 4, 1, 1, 4, we see these two column vectors here run in the directions we found. This is the northeast southwest direction, and this is the direction orthogonal to that. So that makes sense. If we look at -2, 1, -1, 2, then we once again see some directions that were the directions we found. So this is 1/4, 1. This is pointing sort of more east than north, and this is just flipped around the other way. Notice as well that we have a negative eigenvalue here, and that's corresponding to the flip action with respect to that eigenvector. So we can tell that the plane is preserved along this direction, but it gets flipped along that direction. And then finally, if we look at 2, 1, -2, 2, then what we're going to see is that actually we get complex eigenvectors and complex eigenvalues. So this IM in Julia is the imaginary unit. And this is telling you that there are no real eigenvalues, which is consistent with what we saw with the rotation action of that transformation. Okay, so let's look at problem 2. This problem deals with repeatedly applying a transformation to a vector. So you're going to start with a more or less arbitrary vector and repeatedly apply a transformation A to that vector. And that's a very basic thing to do if you have some system that's has a time step described by the application of a linear map, and you want to see what happens in the long run. You want to repeatedly apply that map and see where the various starting states end up. That's sort of a natural and canonical thing to do. And in this exercise, what we're going to see is that eigenvectors emerge from that. Even though we don't start out talking about eigenvectors, they show up in the problem. So the basic setup is that you start with a vector v0, and then, as I said, you repeatedly apply A. You also normalize. So we have this denominator here. That's really just a bookkeeping measure to keep the vector's length from getting extremely long, where the numbers would be so large we wouldn't be representing them very accurately or even at all in the computer. But basically the idea is just repeatedly apply A. And then see where that vector goes. So what is the sort of ultimate direction that you're converging towards as you repeatedly apply A? And the punchline is that the direction is that of the eigenvalue, the eigenvector with the largest eigenvalue. So let's take a look at how that works. So we know that A has a basis of eigenvectors because it's symmetric. And the key idea is to take the vector v0 and expand it with respect to this eigenbasis. So it's going to have some coefficient c1, c2, and so on up to cn. And we're going to repeatedly apply the matrix A and see what we get. So if we apply it once, then A is going to distribute across these terms because A is a linear transformation, And when A hits each of these eigenvectors, it's going to kick out the corresponding eigenvalue, because A times any eigenvector is equal to that eigenvector times the eigenvalue. So we're going to get C1 lambda 1 U1 and so on up to Cn lambda n Un. And if we applied A k times instead of just once, then we would just get k factors of lambda on each term instead of just one. Again, just repeatedly applying A. And the idea here is that if one of the eigenvalues, let's say lambda 1, is larger at all than all of the other ones, then that term is going to dominate. So this first term is going to end up being much, much larger than the other terms because of exponential growth. You have a larger base and you're going to grow much larger. The way to get a hold of that is, so first of all, we're going to normalize this result by its length, just to get a unit vector. So take this vector and divide it by its length. And then one nice way to explain this sort of term dominant behavior is to normalize it to make it constant and do the same thing in the top and bottom. So we're going to multiply by lambda 1 to the minus k. And again, we're assuming that lambda 1 is the largest eigenvalue in absolute value. And then distribute that term through. So in the top, the part that's growing with k goes away, and you just end up with c times e1. So that's a constant now. And then the second term is going to be c2 times lambda 2 over lambda 1 to the k times u2. And now, if we take k to infinity, then these terms will all go to 0 because it's a number less than 1 in absolute value being raised to successively larger power. And that's going to converge to 0, while the remaining terms here out front are constant, so they stick around. And so we can say that as k goes to infinity, this converges to C1 U1 over the length of that, which is just going to be the direction of the leading eigenvector. So notice here that we're assuming that the component C1 of the starting vector is non-zero. If it were 0, then that term would go away and the behavior would be dictated by the second largest term. Okay, problem 3, we're going to talk about the singular value decomposition. So the idea of the singular value decomposition is that not every matrix A has an eigendecomposition. As we saw above, a rotation matrix has no eigenvectors, for example. Furthermore, if a matrix isn't square, then it doesn't even make sense to think about an eigendecomposition. However, what we can do is form the matrix A transpose A, and that is going to be symmetric and positive semi-definite, and so it will have an orthogonal eigendecomposition. And then the amazing thing is that actually, if you take the square root of that matrix by just square rooting its eigenvalues, then the resulting matrix is just the same as the original matrix up to a rotation. So you have to apply some angle preserving and length preserving transformation of space in order to make them actually line up, but generally it's the same thing. The distortion of space is the same. So in exercise, we're just going to look at a few examples and reflect on how they're related. So we start with this matrix 1, 2, 1, 1, and what we can see is that the images of the grid lines under these transformations, they give the same shape except it's rotated. And we can just try all sorts of different values here, and it's always going to be the same thing. If we look at the identity matrix, if we reflect, or any way you want to change these numbers around, if it's singular, they're always going to be related by a rotation. So let's take a look at the singular value decomposition, the way it works out. So the idea is that in this polar expression, so it's called the polar decomposition, R times square root of A transpose A. If we take this part and eigendecompose it, then there's going to be an orthogonal matrix that splits off to the right, and the transpose of that splitting off to the left, and we combine that with R, and we end up with two orthogonal matrices being multiplied together, which we combine into a matrix we call U, and then we have a matrix, a matrix called V on that side, and that gives a way of thinking about the transformation A, which has a lot of value in applied context, really quite a variety of contexts. So let's take a look at a picture of that, so we can really break it down. So we have up here a matrix 1, 2, negative 1, and we're seeing how it's transforming space. And the punchline is that we're going to be able to put down a square grid, not necessarily running along the axes, but a square grid on the domain side that gets mapped to a rectangular grid on the codomain side. So that's going to be telling you in what directions A is stretching space the most, and in what directions it's stretching space the least. It gives an easy way to think about how it's transforming areas, because each square over here gets mapped to a rectangle over here, and so if we just know the dimensions of this rectangle, that's telling us how areas are being transformed. So anyway, piece by piece, the way it works is the first thing that gets multiplied in the SVD is V transpose. So we're working right to left, because that's how function composition works. So if A is equal to U sigma V transpose, then we need to think about each application one at a time, starting from the right. And the idea is we're gonna take grid lines running along the axes down here on the codomain side of V transpose, and then map them back up to the original space. So there's going to be some rotation there. So V transpose is an orthogonal transformation, so the square grid gets preserved as a square grid, but it rotates. And then once we get here, we're going to apply the diagonal transformation sigma, and that's just going to stretch space in two different directions. So it gets stretched more in the horizontal direction than the vertical direction, because 2.3 is bigger than 1.3. And then finally, U just takes that picture and rotates it to give the final image of all the points that started over here on the domain side of A. And there's some important things to read off this picture. For example, if you want to know these directions, so the direction of maximum spread here, then you should look at the image of the positive x-axis under the transformation U, and that can be read off of the matrix U by just looking at the first column, since this first standard basis vector E1 is going to get mapped along this direction. And similarly, if you want to know this other direction, then that's going to be the image of E2, which is the second column of U. So columns of U are telling you the axes of this ellipse on the codomain side. And likewise, the axes here are going to be specified by columns of V, because we want to look at where E1 and E2 going up from the bottom of the picture to the top. and that's going to be specified by columns of V transpose inverse, since V transpose is going down and we want to go back up. But since V is orthogonal, V transpose is its inverse, so that's the V transpose inverse is just V. So putting it all together, the columns of U tell you the axes of the ellipse over here. The columns of V tell you the grid lines over here that map to those grid lines. And the entries of sigma tell you how each stretching happens along those two directions. So the purpose of this problem is to start thinking about how computation looks different when you do numerical linear algebra than when you're doing linear algebra and introductory linear algebra course. So row echelon type operations are not a good way forward when you're doing numerics, because it becomes very difficult to see whether a particular number is actually zero. You're in most cases doing arithmetic only approximately in the computer, and questions about whether an entry can serve as a pivot when you're doing row reduction become trickier. So a nice robust way to do it is to use the singular value decomposition instead. So null space, for example, it does use the singular value decomposition if you check out the source code in the standard library. So let's just quickly take a look at that. So you can see there's very little code here, and it's using the singular value decomposition. So let's just see how it works. So if we start with the identity matrix, we should get nothing, and we do. We get a matrix that has 3 rows and no columns, indicating that there are no dimensions to the null space. And if we make sure that it has a null space, then we start to get more columns showing up. So for example, if we leave that last row empty, then 0, 0, 1 is going to span the null space. And if we do something like make all the entries the same, then the rank is going to be just 1, and the null space is going to have dimension 2, and we're going to get a pair of vectors that span the null space. Similarly, if we want to calculate rank, we want to look at the first so many columns of the matrix U. And the reason for that, if we briefly look back at this picture, is that if you have some 0 entries in sigma, that's going to squish those dimensions out. The second singular value is 0, then all these points above the axis get smashed down to the axis. All the points below get smashed down to the axis. And you end up with sort of a degenerate ellipse over here that's just like a line segment. And then U is going to put that up here on the codomain side somewhere. So all the dimensions after the last one that's non-zero don't end up getting represented here in the codomain, and all of the other ones show up here and then get mapped by U up to the this top right part of the picture, and they span some space, and that space is going to be the range of A. So we just detect how many non-zero singular values there are. So the rank function does that for us. And then we look at the first that many columns of U. So for example, with this matrix of all ones, we get a rank of 1, and the first column of U, it has a vector in it that has all of its entries the same. So that's parallel to the 1, 1, 1 vector that spans the column space of A here. Let's move on to problem 5. So this problem addresses one of the most important aspects of the singular value decomposition, which is that it gives you a way to find a vector subspace which minimizes the sum of squared distances to a given set of points. So let's look at that in a really concrete case here in the plane, where we have these 5 points, 3, 4, 2, 1, 1, 3, and so on. And we're going to plot these points in the plane. They look like this. And we're going to be looking for the one-dimensional vector space. So in other words, the line through the origin, which does the best job of approximating these points in the sense of having the minimum sum of squared distances to the 5 points. So we're going to draw a line sort of cutting through here, and the idea is that the sum of squared distances to those 5 points measuring directly from the point to the line is going to be as small as possible. So let's take a look at that. So if we have a point here, call it A, and we want to know how far it is to the line through the origin running along the vector, let's call it V, then so we want to know this distance. What we can find more easily is the other leg of this right triangle, which is going to be just A dotted with V, because we're projecting onto a unit vector, and to project a vector onto a unit vector, you just compute the dot product. And so that means by the Pythagorean theorem, this distance is going to be the square root of the hypotenuse squared minus the other leg squared. So the sum of squared distances is going to be the sum of this expression here over all the points. So it's going to be a1 squared minus a1 dot v squared plus length of a2 squared minus a2 dot v squared, and so on, and up to a5. And we see that some of these terms don't have v in them at all. So if we're trying to find a v that minimizes this sum of squared distances, then none of those terms matter. We can just focus on the other terms and try to minimize them. So the punchline there is that we're trying to maximize these remaining terms. However, note that that expression can also be rewritten as the squared norm of AV, where A is the matrix whose rows are A1 up to A5. So in other words, we want to maximize how much A stretches a unit vector V, and we've already seen that the singular value decomposition tells us something about that. The vector that gets stretched the most is the first column of capital V, the matrix in the singular value decomposition. So let's implement this a couple of different ways. One sort of by hand, and the other using the singular value decomposition. So here's the by hand way. So what we see is that the line of best fit has a 46.9 degree angle with respect to the origin. So it's moving up at a slope slightly greater than 1, which makes sense in the picture. But we could also calculate this using SVD. So we calculate the SVD of A, pull out the V matrix, and look at the first column. And then if we want to translate that to an angle, we can calculate the arctan of the y over x ratio there, and then switch to degrees like we did before, and we get the same answer.